gravity, it can be included in some fashion. Okay, now the Snyder model is one of the first, but actually this model, if I understand it correctly, isn't really a model of space-time algebra. What it says is that the x coordinates can be embedded inside a bigger group of angular momentum sort of generated. It was very much based by the de Sitter algebra, Poincare group with the de Sitter algebra. So it's really part of a larger algebra which includes rotation generators. But it was adapted by Doppler, Fredenhagen, and Roberts in some version fairly early on. Now, the quantum group models, maybe opinion differs, but the first paper I know of was my own paper, which uses quantum groups to describe Planck scale physics. That's in this paper here. And where I was coming from was this class of new quantum groups called bicrossproduct quantum groups. And the first space-time model coming out of that is really this one, which is with Henri Ruegg. And so I'll say a bit more about that. There are many others, Doppler, Fredenhagen, and Roberts, papers by Western collaborators. Then there's quantum field theory on those flat spacetimes, notably Harold Grosser, for example, but many people, many of whom are in the audience, quite possibly. There is quantum gauge theory, etc. So there's a whole gap here. I'm just skipping over all that. Then, now the thing about these models is they're all flat. They're Minkowski space models, guided by quantum group symmetry, as to provide the structure for the model. Now, what you really want to do unified quantum theory of gravity is curved models to be convincing for this purpose. This purpose that was discussed. So that required a development of some kind of formalism of non-commutative or quantum Riemannian geometry. And I'm going to use a particular one, which was developed, it builds on works of many people, including Dubois-Violette and others. But it's going to be a bit different from Alain Cahn's approach. And it's, but using that formalism, which is described in this book here, the first models in that formalism appeared around 2013. And actually it was the same algebra, but this algebra was equipped now with a quantum metric. And it turned out quantum metric could not be flat. Within the constraints of the mathematics of quantum Riemannian geometry, Minkowski space is not actually a possibility. It actually has to be a bit curved. And that curvature is forced upon you by the non-commutativity. And then that same formula can be applied to the discrete case. You get quantum gravity, for example, on a graph. And this actually is no longer just modeling spacetime. It's actually saying, well, if that's a better model of spacetime, for example, a square graph, then let's start to do quantum gravity on that better model. So that actually is quantum gravity. And then last year, we had papers on quantum gravity on a polygon and some other work, which I will be describing in more detail with my graduate students. Okay, so that's the picture. Feel free if people want to interrupt me, otherwise I imagine there'll be time at the end. Now, since I was told to start fairly gently, I'll just remind you what is a quantum group, very roughly. It's an algebra with a unit. There is a coproduct which kind of unmultiplies things, it goes the other way. And there is something which plays the role of inverse called the antipode. And the only thing you need, the most important thing in my perspective of what a quantum group is first is that it's self-dual. So the same maps, when dualized, give you a very similar structure on the dual, but just be careful. The dual of M star actually lives in this space, which is slightly bigger than A star tensor A star. So it doesn't necessarily restrict. So to do it properly, you will need some kind of topology or topological completion. I'm not going to worry about those things in a physics talk, but the experts will know that there are a lot of issues to be dealt with. In the same vein, the C infinity vector is not really a Hopf algebra, but it can be completed into a Hopf algebra in an appropriate way. So that's an example. But I wrote it here because the coproduct is going to be a function in two variables, two copies of C of x. So it's going to be a function of x and y. And that function is the value of f at x times y, where we use the group structure. So you see how a group structure is encoded in the coproduct. The other one, basic example, is an enveloping algebra of the Lie algebra. That is an honest quantum group, but not very interesting one. Then more interesting ones were discovered by Drinfeld and, well, by the Russian group coming out of integrable systems, Kulish and Sklianin, and by the Japanese group, notably Jimbo, for all G semi-simple, and corresponding coordinate algebra, which is kind of dual to them. They are also known for the standard groups of standard Lie type. Now, bicrossproduct quantum, well, my own contribution was another class of quantum groups different from the Drinfeld ones, which are these, and they kind of smash in together the first two examples in this funny way. And they have a different role in physics. They're not so much in integrable systems. They're more to do with Poincare groups, because these are deformations of inhomogeneous quantum group, inhomogeneously algebras, enveloping algebras. So for example, the Poincare group. So that seems to have turned out to be their role. And that actually was what I proposed back in 87, 88. And in that old paper, I gave you this example, just where everything is one-dimensional. So you've got polynomials in X, polynomials in P, and, well, not really polynomials, but something like that. And here we see the commutation relations. They are a deformation of the Heisenberg commutation relations by something which has some kind of macroscopic horizon length, curvature length, RH. And in the other limit, where h bar goes to 0, this becomes classical, but this coproduct is still there, and that it depicts a non-commutative, a non-abelian group, which is R cross R. So that's an example that unifies quantum theory and gravity in some sense. There's a curved space, or phase space, and a quantum algebra. The key thing about this model is it's self-dual. So the dual is of a similar type with different roles for H bar and RH. And physically, the observables would live in here. Therefore, the states would live in the dual. So this kind of duality where you interchange X and P, which is quite fashionable these days, is what I talked about there. I call it some sort of Born reciprocity. And it actually is implemented by Hopf algebra duality. Okay, so that's what I want to take away from that old paper. Another thing that happened since then, again, I'm not going to spend a long time on this ancient history, but where these things really came into their own was more complicated models like this Poincare model, Poincare quantum group. Here, the space part is now R cross R3, so a non-abelian group, and the rotation part is the undeformed Lorentz group, and this forms a quantum group. And this acts on this particular space-time. I didn't put the xi's commute, and the t doesn't commute with the xi. So this is the model that Ruegg and I introduced. This Hopf algebra itself wasn't new at the time. It was first found in a different way by Lukeski et al. As a contraction limit of UQSO323, but it arises naturally this way. What's important is that it acts on space-time. This comes out of the bicrossproduct model. Now, acting on space-time means we can look at plane waves like this, and then there's also a natural quadratic Casimir. And this leads you to variable speed of light predictions. And this was analyzed, it was first speculated by Giovanni Amelino Camiglia, and then we wrote a paper explaining it in more detail. And you do get these measurable effects for a difference of frequencies for low energy and high energy gamma rays from gamma ray bursts that travel cosmological distances. So because they travel cosmological distances, this number is quite large, and that offsets the Planck scale. So you get something reasonable, and that is, I don't think it's likely to ever be detected experimentally. You need a lot of observations to detect it, but in principle, it could be detected. Now, the other feature about this model, which makes some people say it makes it doubly special, is that the Planck model, there's the momentum sector, the coordinate here, the p coordinate in front of the x, this is bounded by 1 over lambda p. Okay, now more interest perhaps, or sort of a different stream of thought, but fits in exactly the same way, is 2+1 quantum gravity. And so Atuf was the first person, I believe, to speculate that in 2+1 quantum gravity, well, Euclidean 3D quantum gravity, there should be some kind of model position space, which actually you recognize this algebra is actually the angular momentum algebra. We call it fuzzy R3. But it's regarded as coordinates. And what that means is, under Fourier transform, a non-commuting position space, like an enveloping algebra, corresponds on the dual side to a curved position space, namely functions on the curved SU2 manifold. And that was studied a bit more in my paper with Laurent Friedel. So so we have actual models in 3D, we have speculations in 4D with verifiable consequences. It's been like that for some years now. I don't know what the latest progress is, but I'll come back towards what we could do next in these models at the end of my talk. I have time. Okay, so that's the end of that introduction. Now, what I want to do is fast forward now about 30 years or 20 years to 25 years to curve models. So to describe that, I first got to describe what is quantum Riemannian geometry. So this is going to be the framework. And again, I apologize to experts in the audience. So the idea is we take classical functions on a manifold and we focus on the exterior algebra. So particularly the one forms. So the one forms are things like dx. There's a map D which turns a function into a one form, which is given by this formula. And differentials and so one forms and functions commute. And they extend to whole exterior algebra, where D extends by obeying the graded Leibniz rule. Now, what we keep from all that in the quantum case is we drop the algebra being symmetry, and it can now be any unital algebra. It doesn't have to be commutative. We drop the graded commutativity of the wedge product. It doesn't have to be graded commutative, but we keep the associativity rules. In particular, omega-1 is a bimodule. That's really part of the associativity of the exterior algebra. So we have a differential graded algebra. We have a map D, which obeys the graded Leibniz rule and extends to higher degree. So that's the setup. Well, I won't worry about inner, it's not relevant to today's talk. Now, what about a metric? Okay, so in this, and here we start to differ from Alain Connes and many other people, is we think of a metric the same way as physicists think of a metric, namely a tensor. So G is an element of omega-1 tensor over A omega-1. So physicists would write something like this, ds squared, this will be the metric, right? But this nothing written here is really tensor product over C infinity of M. So there's a tensor product over C infinity of M hidden in the physicist notation for metrics. And we just have to make that explicit. Then there should be an inverse metric, which goes the other way. So a metric in a product on one forms, if you like. And they should be inverse to each other, which is what I've written in this diagrammatic way. So you read down the page and then it reads like the usual thing that says this is inverse to this. It gives it the identity map. Okay, so now one thing which is not at all obvious, I think some referees still don't believe it when we submit our papers, is that when you impose these conditions, they look very innocent, but actually, if this inner product is going to be a tensor, so strictly tensorial, a bimodule map, then it actually forces G to be in the center. So it commutes with functions. So even though we're trying to do geometry, we have a constraint on G, which you can view either positively or negatively, depending on which side of the bed you woke up, fell out of. Now, but let's not worry about that. There are lots of examples in any case, even with central metrics. The connection, a Levi-Civita connection is going to be, well, a connection is going to be a map like this. Now, normally you would think of a covariant derivative as a map, let's say for every vector field, we should have a map from omega-1 to omega-1. So that's just going to be evaluating against a one form. Then we would have a map from omega-1 to omega-1. So the Leibniz rule properties for a covariant derivative become this abstractly. But because we can also multiply from the other side, we also need compatibility. So we say we have a bimodule connection if we also got a Leibniz rule on the other side with respect to some bimodule map sigma. So this is the gadget that goes back to Peter Michor and Michel Dubois-Violette. I forgot to write that there. Now, the thing about bimodule covariant derivatives is that they extend to tensor products. So the way that you act on a tensor product is you act on one factor, you act on the other factor, and then you use sigma to bring things into the right position. So the far left here, so acting on a metric G, G is in omega-1 tensor omega-1. And the way that you act on it is you act on the left factor, you act on the right factor, then you use sigma to put the place where the vector field would evaluate to the far left, so that both terms have the factor to the far left as the place where you'd evaluate against a vector field. Otherwise, it wouldn't be consistent. And with that definition, you have a covariant derivative on omega-1 tensor omega-1, and everything works nicely. And so now we know what we mean by nabla G is 0. So we define a Levi-Civita connection as torsion 0 and metric compatibility tensor 0. And here torsion, again, it's not something you would normally see if you're a physicist, you would see it with lots of indices, but abstractly, the meaning of the torsion tensor is it's really a tensorial map. Well, it's actually here, it's a left modular map from omega-1 into omega-2, which is defined as the two ways to go there. You can either go directly with D, or you can go to omega-1 tensor omega-1 with nabla and then apply the wedge product. So those two different ways to commute, that's being equal, that's what zero torsion means. And the other thing which you would normally do with lots of indices is the Riemann curvature. So Riemann curvature in our language, read down the page, is you apply nabla once, and then you apply nabla twice, basically. That's what this term is. And then you have to compensate a little bit with D to make things work. And then you get a tensor, you get a left module map. One other thing we need for this talk is we need to read the Ricci tensor. Now, I won't lie to you, the Ricci tensor that's in the book with Edwin and that's in all our papers is a working definition. I don't think it's the final definition, but the working definition is we copy the physicist definition. That's always a good start for a working definition. So the physicist definition is you apply the Riemann tensor and you take a trace. But how do you take a trace? Well, you have, before you can take a trace, here's omega-1. The output of our nabla is in omega-2 tensor omega-1. So to take a trace, you have to first lift omega-2 into omega-1 tensor omega-1. So omega-1 tensor omega-1. So now you've got something over here with three free indices, omega-1, omega-1, omega-1. And now you can contract those indices. And the one deficiency of this approach is that the natural thing to do is to contract the input index of Riemann with the first index, which is not what you do in textbooks. So we get a minus sign relative to textbooks, but there's no rationale to putting it over to the other side. That would just be awful. And the other thing is that the lift map classically would send a two form, let's say omega wedge eta, would go to omega tensor eta minus eta tensor omega. So it'd be the antisymmetric lift, but divided by 2 in order to project back. And that half also is built into this definition. And that means that our Ricci tensor is actually minus a half times the classical one. So when comparing our results with physics, remember there's a minus a half difference. Okay, now we're going to apply this to the fuzzy sphere. This is in my paper with Evelyn Lira-Torres. Well, the fuzzy sphere itself has a long history. The fuzzy sphere is just the fuzzy R3, the 't Hooft algebra, angular momentum algebra, but with the sphere relation. I've used certain conventions where I've normalized it to bring this out, this number. And this normalization is such that lambda p is not actually the Planck scale, it's actually a dimensionless number. Probably a mistake, but anyway. So it's a unit sphere deformed by a dimensionless parameter. And this is normalized so that if lambda is 1 over n, then this algebra descends to the n-dimensional representation of SU2 to give you the discrete fuzzy spheres. That's why we did that. Anyway, now the new thing we're doing is the differential calculus. So this is taken from my book with Edwin. We introduce omega-1 to the one forms by declaring a central basis, SI. So they commute, and this is then the differential. So that defines, the differential calculus. And we extend it to a whole differential graded algebra by saying that the SI is anti-commute. And D extends like this. So that's a particular definition of omega-2, of omega-n. And that seems to be the nice one. I mean, there are other ways you could do it. What's a little bit alarming here is that this actually is three-dimensional, not two-dimensional. But there's a reason for that. Many non-commutative calculi actually have an inner element. Actually, I was going to skip that. But anyway, there's an element here which you don't see classically because it would be 0. If these were the, well, this quantity here for a classical sphere would be 0. But because if you take the limit lambda p goes to 0, even if that goes to 0 and that goes to 0, you can still have a non-zero thing. So this remnant is this one it means that calculus actually is three-dimensional, even in the classical limit. So we've got as a kind of extended sphere, but you need that for the quantum geometry to work. Now, a metric is then any real symmetric matrix for the coefficients. A connection, the general framework is, it doesn't have to be, but we assume it has this form, and we look for gamma ij. Actually, we look for ones which are C numbers rather than, because the metric here has to be a C number for centrality. So we look for C number coefficients. And there's a unique one if you impose that condition, which is this one. So there's a natural Levi-Civita connection. Then the curvature, we write it in this form for this particular tensor, whether it's quantity rho ijk. So the formulas look a bit different because our bases are not the usual coordinate bases. So they don't look like usual formulae in textbooks, but they're not dissimilar. Then the Ricci tensor, using the antisymmetric lift of the SIs, has this form. And the Ricci scalar, which is given by contracting the Ricci tensor, then comes out like this. So this final formula is rather surprisingly nice. So you take the matrix for G, square it, take its trace, and take away a half of the trace of the matrix squared, and divide by the determinant. So, and that's a calculation of the Riemannian curvature, the Ricci curvature, Ricci scalar, etc. So comes out nice. So now we can do quantum gravity on the fuzzy sphere. So it's Euclideanized. We're going to integrate over the space G, which I've called P3 here, of 3 by 3 positive definite symmetric real matrices. This is a homogeneous space that can be identified with this. It has a natural metric, a classical metric on this moduli space, which is this one. Now we've got, so that metric is going, when we integrate over the metrics, we're going to have this, we're integrating over the classical moduli P3. So that's easy. But what goes up here? We've got the Ricci scalar, but we need to get a number, which would normally you'd integrate over the manifold. So you have to integrate over the fuzzy sphere. So we don't really know, but we also don't really care because this S of G is a C number. So it's not actually a function on the fuzzy sphere. So all I've got to do is to declare the normalization, and then I've defined it on all C numbers. So I don't really know or care what integral is on any function, but for my particular type of functions, which are constants, I just got to give my normalization. And I choose my normalization to be this, which is not too different from what you might do if you were really doing integral over a manifold. You might have a half here rather than det G, but then the dimensions aren't quite what you'd expect anyway. So this is the one that gives you nice answers. So that's what we take. So that's nice because that cancels out from the determinant in here. So now what we've got is, this is the action for quantum gravity. This is now the integral over P3, this classical moduli space, with the Jacobian for this metric. The Jacobian for this metric on P3 gives you this, so that goes in there. You can write that determinant as a bosonic integral if you want, over a vector coordinates, xi. So that is quantum gravity on the fuzzy sphere. Now, to calculate it, we use Euler angles, and so we write everything in terms of these guys, in terms of these angles and the normalizations, the eigenvalues of G. So you can sort of break down the information in Gij into a spherical angle coordinates plus the weights to assign, which are the eigenvalues of the GIs, the lambda 1, lambda 2, lambda 3. And so that's a classical calculation. That works out to be that. And now we're going to focus on, if we're only interested in observables which are independent of the angle. So spherically symmetric observables means they're just functions of the lambda I. So we're just going to focus on that for simplicity. So then the effective partition function becomes this. Now, again, it's still infinite. We've got a divergence at epsilon at 0 for lambda I, and a divergence at infinite lambda I. So I'm going to cut off the large ones, and I'm going to have a epsilon for the small ones, for the small end. But even though those things are infinite, so you should really apply renormalization, etc. But certainly in our paper, mainly because I don't know enough physics to do the normalization properly, we take a shortcut, which if we just look at ratios. So it turns out that if you're interested in expectation values, you're not interested in Z itself. So even though Z itself diverges, the ratios, the epsilon drops out. So we don't even care about that. So then, for example, this expectation, which is Z what with the factors lambda, then divided by z. That ratio, the epsilons cancel out. I mean, the divergence epsilon disappears, and we just get something divergent at the top end, at large lambda. And then if we look at, and that seems to be quite a general phenomenon. So all the models that we've computed have the same phenomena, that we still get divergences at the upper end, but those divergences also can disappear if you only look at ratios. So if we look at the ratio of sort of the relative correlation functions, then you actually get well-defined numbers. So for example, there is the uncertainty sigma of the lambda i's divided by the average value of the lambda i's is this quantity. So that becomes an exact calculation, independent of the regulator. Or let's say this is in the large L limit, but you get nice answers. Okay, so that's what I'm going to say about that model, because I want to show, there's so much I want to tell you today. Okay. So let me just go through this very, very quickly, just to say the same thing happens if you look at Zn. So we have the functions now. The algebra is functions on Zn, and the only difference here is that instead of a central basis, the natural basis of left invariant one forms, this is a group, and so that has left invariant one forms relative to the group structure, and these are E plus and E minus. And instead of being central, they commute, where they non-commute. When you move F to the left, it gets shifted. R plus or minus are the shifts by plus or minus one operators, and the differential becomes these finite difference operators, where this D plus or minus is the shift minus identity. But aside from that, we can use the same formalism. A metric has some coefficients in my basis. I demand that the lengths in that direction is the same as the length in the other direction. The lengths are independent of the direction of the arrow, and that gives you a constraint on the B. So the B's are given by A. So now everything's dependent on one function A. That's the content of the metric, is a single function over the polygon. I define this ratio rho, and then the Levi-Civita connection comes out to be this, which is scalar comes out to be this. And what's quite amazing is if you take this measure, which is like determinant of G for the measure, then the action, the Einstein-Hilbert action, looks exactly like a scalar field. It's rho D plus plus D. So D plus plus D minus is a standard discrete Laplacian on a lattice. Okay, it's just double derivative. Well, it's f of x plus I plus 1 plus f of I minus 1 minus twice f of I. So that is really amazing. So quantum gravity is a scalar field theory, except it isn't, because this rho is bigger than 0. It's not a real or even not a complex or real field. It's a R bigger than, it's a tropical field. It's R bigger than 0 field. And not only that, because of the ways that these are defined as ratios, their product is 1, so there's a constraint. So actually the measure has to include the constraint, very similar to what we just did. So when you take that constraint into account, then you can do the thing, and we get very similar results. I just want to shortcut straight to the answer. We have the same thing here. The variances have a kind of well-defined limit for these ratios. Okay, I'm going to just leave it at that because I've run out of time. Well, I wanted to show you one thing. That was for n equals 3. For the general case, it's easier to analyze a relative version of the theory. In the relative version, we don't look at the AI, but the AI divided by the geometric mean. So we changed, instead of the AIs, we work with the BIs, B0 and B1, and the geometric mean. And then when we do the integrals, we don't do the A integral. And that gets rid of, that's a different way of handling the L divergence. Now you get well-defined things, because the L divergence, which you're always going to get in quantum gravity models, is from the scale symmetry. So you'll be able to always scale things, and you're always going to get a divergence from that. But by focusing on the relative metric sizes, and we have the overall scale set by the geometric mean as an independent variable, and not doing the A integral, we don't get the divergence. And so then we got a relative theory, and these are the correlation functions up to n equals 6, which behaves somewhat similar to a particle in a box of size n. It's quite reasonable, but instead of exponentials, you've got sine or cosine for this behavior. Okay, let's leave it at that. Now, what I want to tell you about in the remaining of the talk is stuff that is a preprint. So that all of that's been published, and I should have said, I forgot to say that, but when I did the second model, the gravity on Zn model, this was in my paper with Julio Agoto-Quiroz, published here. And so our follow-up paper, we don't do quantum gravity. We're now going to look at quantum geometry. So for those of you who are interested in quantum geometry, non-linear geometry, this is perhaps more interesting. We're going to look at black hole type models. So we're going to look at static metrics of this form, where G is going to be a fuzzy sphere metric. So it's going to be at each point in R, so R and T are going to be classical. At each R and T, we're going to have a sphere, but that sphere is not going to be an ordinary sphere, it's going to be a fuzzy sphere. And so its geometry is going to have a 3D differential calculus, which is the one we just studied in previously with the SIs. I'm even going to focus for today's talk just on the diagonal, the round metric. So I'm going to have Gij is going to be delta Ij times a constant that we put in for convenience, a constant k. And that is to make the solutions look nice. So then, when you solve the system, you find the Lever-GVD connection for this in general. You then ask which of those are Ricci flat, and we get an answer. And it turns out that beta has to look like this. And this is to be compared with the usual one for a black hole, right? Usual black hole has RH over R, but this is squared. And you have to have this constant k. This is the connection. This is the, now I'm going to focus, there is curvature, it blows up at R equals 0. I'm going to focus, to extract some physics, I'm going to focus on the Laplacian. So the Laplacian again comes out of the quantum geometry. You apply nabla to d of a function, and then you apply the round bracket inner product. That gives you another function. That's the Laplacian, Laplace-Beltrami operator. And that looks like this. Now this actually, this form of metric here, not this bit, but this form of metric here is exactly what you have for a 5D black hole. This is the Tangellarini solution for a black hole in 5 dimensions. So we have exactly the same radial form as a Tangellarini black hole in 5D. And the only difference is that where you would normally have the 3-dimensional Laplacian on each S3, we now have the fuzzy sphere Laplacian on each fuzzy S2. And this is given by the double derivative this is the quantum derivative, the di's defined by with respect to the basis SI. Now, a word about that fuzzy sphere metric. It looks innocent enough. It's just SI tensor SI. It's rotationally invariant, natural round metric. But when you decompose it in terms of the things, we actually have it looking like this, where I've defined theta to be this ratio. Now, this guy still has a ratio as lambda goes to 0, which is a kind of normal direction. So what this really is the geometry of the fuzzy sphere is really an ordinary sphere, but with an extra tangent direction, which is normal to the sphere when embedded in R3. This is very similar to what happens in 3D in the Chern-Simons theory for 3-manifold invariance, where knots become frame knots. As well as the usual knot direction, you have to have an orthogonal direction, which is the framing. So in the same way here, the quantum geometry forces upon you an orthogonal direction, which is an extra direction in the cotangent bundle, and that's this theta prime here. And so what that means is in the classical limit, this metric is actually 4-dimensional. And so that's the origin of this phenomenon. It's what we call dimension jump. That the behavior of the 3D black hole, the model, the usual black hole in 4 dimensions, but with a fuzzy S2, looks more like a 5D black hole, the dimension jump. Now, and one way you can, and now the radial part is the same as a 5D black hole, but the Laplacian is not. The Laplacian is the one for the fuzzy sphere. But the one for the fuzzy sphere is not too daunting. It turns out to have the same eigenvalues as an ordinary sphere, namely given by integers L. Just the difference is the eigenspace of orbital angular momentum L is given by antisymmetric tensors, totally symmetric traceless tensors F, but these xi's are non-commuting. That's the only difference. So it works the same way as these would normally be this would be an alternative basis to the basis of spherical harmonics, but now they're non-commuting. So therefore we can proceed and solve the system. We just work in each eigenspace of fixed L. Now the first thing we're going to do is we're going to solve for the Klein-Gordon equation to extract the physics. We're going to solve the Klein-Gordon equation relative to a free field. So we're going to sort of look solutions of this form, e to the IMT times psi L, where psi is slowly varying. So this would what you would do in flat space quantum mechanics. To get quantum mechanics out of the KG equation, you would take this kind of approximation. If you do that, then gravity will enter as a potential. And indeed it does, because if you make that approximation, stick that into the Klein-Gordon equation, then you obtain, and throw away double derivatives in psi, in t, psi double dots, then you get this, which is some kind of, it's obviously it's a bit curved because, but it's some kind of spatial angular momentum plus this interaction term, this potential term. And this potential term looks like this. Now, so this is the effective gravitational potential experienced by a particle as extracted through the Klein-Gordon equation. Now, I realize this is not a standard thing to do. I haven't seen this in any textbooks, but I don't see why you can't do it. If you were to do this for an ordinary black hole, Schwarzschild black hole, what you would get would be GM, capital G, capital M, M over R. You get the usual gravitational potential for a Schwarzschild black hole. I've taken the same RH as for a Schwarzschild, but so imagine that there's a particle we thought was a Schwarzschild black hole, but it isn't. It's actually a fuzzy one, and then we would see this in this inverse cubic law for the gravitational force. So what I'm saying is that fuzzy S2 has observable consequences. They're a bit more drastic than we would have hoped, but maybe there's still some role for this kind of behavior in model building. Okay, now the other thing you can do if you're doing ordinary physics is you can say, well, I'm not interested in gravity because that's an illusion. I should be looking at geodesics, which are falling, which are in free fall, for particles in free fall. So then you will only see tidal effects. Now, the way that we do that in the Schrodinger approach, again, I haven't seen this in any books, but I think it's a reasonable thing to do, is we first give ourselves some base solutions, because e to the IMT is not actually a solution of the Klein-Gordon equation. It's just something I forced into the picture to make it look like quantum mechanics. If I actually look for an actual solution, I can solve for it, and I find them. I can find lots of those. I look for ones with L equals 0, and that's going to be my base one. I actually take omega to equal m. That's going to play my role of my e to the IMT, but this time it's going to be an actual solution. And then relative to that, I look at slowly varying products of that. So when I do that, I'll now get this effective Schrodinger equation where whatever I've chosen for phi will enter here. And so, for example, if phi was a constant, as it would be in flat space Klein-Gordon equation, I wouldn't have this term. I just wouldn't see anything. I'd see free quantum mechanics. I wouldn't see any gravitational potential, but I'd still see potentially tidal effects. And certainly, and so let's do that for our case. So for our Tangle-Arini type solution, you can solve phi numerically. It looks like this, phi m, and for large r actually looks like this. You can see that the imaginary part decays to 0, and this other part looks like this. So then your effective Schrodinger type equation, there's a dot missing on the psi, but psi dot looks like this. And so what we have is this plays so gravitational potential now plays the role differently as the tidal effect. And if you did the whole thing for a Schwarzschild case, then at this point, for the co-moving Schrodinger equation, you would have this for your effective, So I don't really know what to make of that. But what you can do is that you can then solve. That just gives you an idea of what's going on. Of course, you don't have to know any of that. You can just solve the system exactly. So if you use an exact solution and then solve for psi, the Schrodinger type equation, that's this equation here, for an exact psi. You have behavior like this. Here we took a Gaussian and then we evolved it. So the Gaussian on at t equals 0, we take a Gaussian at radius here 5 RH. We'd have a Gaussian and then we evolve it in time. And what you see is a Gaussian, it ends up turning into a radiated wave coming out. And this is for the ordinary Schwarzschild case, and there's a similar picture for the Tangle-Arini one. Okay, I've got a bit of time left, and I want to just tell you about a couple of other models. So also in the same preprint with Julio, we look at one dimension down. So we take at each R and T, we're going to take a discrete circle, or rather a Q, what I call a Q circle. So before I explain that, I already discussed with you the discrete circle, the polygon Zn. That has a nice quantum geometry. So we take the round metric on the quantum geometry. That means equal length for the polygon edges. And then we take the limit n goes to infinity. And what we obtain is something which we call the Q, well, it's literally a cutiform circle. So the algebra becomes polynomials in S and S inverse, which physically you could think that S is e to the it. So these are the trigonometric functions. E to the I theta, theta is the angle. So this is a circle algebra. And the two directions, E plus and E minus, in the limit become F plus and F minus, and they enjoy these commutation relations. These are quite bizarre. S going past F minus gives you minus SF plus, and S going past F plus gives you SF minus plus this Q term. And the meaning of F plus is it really is the differential of S. It's S inverse ds. But the meaning of F minus is it's S ds inverse. And you might think, well, ds inverse and ds should be related, but that's only true if they commute. So if they don't commute, they're two independent directions. And that's why our Q circle has a two-dimensional cotangent bundle. Now, on this bundle, I take my metric. The round metric becomes this metric here. After normalization, I throw away some normalization factor. The Levi-GV connection is very simple. It's just 0 on the F plus. It's just a circle after all. It's very trivial. Now we take that geometry for the angular part, and we go through the same analysis. We take some function here for a static rotationally symmetric solution. We solve for Ricci equals 0, and we end up with a black hole type solution here. We end up with the solution. This is the Levi-GV connection. Now it's a bit more non-trivial. The Laplacian looks like this. There is curvature. The curvature blows up at r equals 0. This is the Laplacian. Now this Laplacian here, instead of being the usual S1 Laplacian, it becomes this cutiform one. And have a look at this. It has things, its eigenvalues here. They're given by integers, L, but the eigenvalue is given by a cutiformed integer. So this is the cutiformed integer of L. And instead of usually, you would have here the double derivative of theta. So that would be L squared, minus L squared. Instead of minus L squared, we get minus cutiformed L squared, basically, something. And otherwise, this part here is what you would expect for this radial classical geometry. This is purely classical. R and T are classical. So there's some classical geometry. Now, this classical geometry looks like the inside of a Schwarzschild black hole, because if you change RH, I just kept it the way it comes out, but if you take RH to be minus RH, so you take RH to be negative if you like, if you make that substitution in these formulae, then these formulae are a limit of the Schwarzschild one. The Schwarzschild one would be beta, beta is the function that goes here, is minus 1 minus RH over R. But if you are well inside the event horizon, then you would be approximately minus RH over R. And that's exactly what we would have, allowing for the minus signs. So with negative RH, this would be exactly we land on exactly the inside of a Schwarzschild black hole, except that the radial behavior is not a sphere, it's actually a circle. The same thing happens for Zn if you don't take the limit, but then the difference is that L goes between 0 up to n minus 1, but otherwise it's very similar features. And this becomes the different formula involving, well, it's a similar formulae. Okay, now I've got one more topic just to say 5 minutes about. You know, you can basically have a lot of fun. The message I want to tell you, if you were just entering this field, and this talk was meant to be addressed not just to experts in the audience, is that we now have the technology. I mean, it's in the literature, the work of a number of people, not just myself and Edwin Beggs, but a lot of it is in the book with Edwin. We have the mathematical technology. What we don't have is the physics, and we can now explore physics. Is the message I want to give you. I've shown you the black hole models. I'm just going to end with Freeburg Robertson-Walker model. So here I'm going to take metric to be like this. T is classical. Here's going to be my fuzzy sphere again, my one-form coordinates on the fuzzy sphere. And I'm going to blow up my unit fuzzy sphere by some parameter, some scale parameter, depending on time, or R. The Levitt-Fichte connection comes out like this. There's a natural one. I should say that in quantum geometry, I mean, there are different setups. There are some competing ones where they've got enough constraints on the geometry that they have a guaranteed QRC. In the bare framework that Edwin and I have been using, there isn't a theorem that there exists a QRC. You have to solve it in every case. But it's remarkably often that you get a canonical, unique, or at least unique under certain reasonable assumptions, QRC. And these models all exhibit that. But there are other models where you have moduli of QRCs. Anyway, this model, we have a natural unique QRC, looks like this. You compute the curvature, it looks like this. I write it in this form, and notice there are various components. Now the Ricci tensor, using the antisymmetric lift for the SIs, the anti-commute and the DTs, I get this, and then this is Ricci scalar. Now, if you write down the naive Einstein tensor, now I say naive because we don't know in general. So where the state of the art is I'm certainly comfortable with Riemann. I'm semi-comfortable with Ricci. I'm very uncomfortable with Einstein because the only formula I have is copying the physics formula. And I'd be okay with that if Einstein was conserved. But it isn't, there's no theorem that it's always conserved. So I'm very uncomfortable with that. But in this particular example, it is conserved. So you'd write down the naive Einstein tensor, and you check that it is conserved. So that's sort of convincing. And then you do the same thing for the stress energy tensor. Again, we don't have a general framework, but you write down the stress tensor for a fluid, compressible fluid, pressure P, density F. And again, you can check that it's conserved. Well, you don't check, you impose that it's conserved. And that gives you a continuity equation, which is this. And then we look at Einstein's equation, again, in our convention, which had -1/2 in the Ricci tensor. That gives you -1/2 in the Einstein tensor. Then the Einstein equation looks a bit weird, looks like this. So we impose that, and that comes out to be this. And now these equations here, this equation, more importantly, how P looks in terms of this one, in terms of F, this actually is exactly the classical 4D FLRW. So we've got the same dimension jump phenomena. If you take this metric, which is the classical FLRW metric with a curvature constant K, our particular K, to fix our conventions, I've absorbed, I've built an R into capital R. So that I've divided through by that to make it fit with our conventions. So in our conventions, this is the usual one in books, wouldn't have the R here and would have an R squared here. But aside from that detail, this is the standard FLRW model. And then that gives you these same equations. So you got the same Friedmann equations. And this is the dimension jump phenomenon that I mentioned. And you do the same thing for Zn and for the Q circle. Okay. I'm in a meeting, James. Okay. So I'm going to stop there. I've run out of time. In fact, my son's just walked into my, well, I've got 5, wait a minute, I've got 5 minutes, sorry. Okay, all right, so I don't need to rush that. Yeah, anyway, so that works. Now you can do the same thing for Zn, for discrete circle. Now, I don't know what these models mean because the radial behavior, what we're saying is in these dimension phenomena is the radial behavior is exactly the same as you would expect classically 1 dimension higher, lower than the one we're solving for. And that has to do with the extra dimension in the cotangent bundle. But of course, the angular direction is not the one you expect. So, I mean, it's not 1 dimension different. So for example, to get the inside of a Schwarzschild black hole, we took a circle at each R and T. So the physics is certainly different. And it would be interesting to do some things with it. Now in terms of what we can do, I want to spend a good 5 minutes on the outlook, because if certainly for a big audience, a diverse audience here, I'm more interested not so much in the details, but it's to convey the state of the art and what should happen next. Of course, this is from my perspective. So firstly, the formalism, even the models already in the literature, there are 3 ones that are written in that I've told you about. One on the square that I haven't really mentioned, one on Z, which I haven't discussed, but it's in this paper, and one on polygons that I've discussed, and one on fuzzy sphere that I've discussed. All of those models can be explored much more. So for the Z, for quantum gravity on the integer line, I didn't do anything other than to write down the action. So the action comes out to be this. So it's a scalar field, but now on Z, not on Zn. And so you can certainly try to solve it, but you've got to deal with R being bigger than 0, and you've got to deal with what is the right measure of integration. And here I think we need some stochastic techniques or something. It's not a trivial problem. So I think that will be very interesting to really try to address that, to take the measure that we integrate over. Then the other thing that we want to do is, I would like to suggest, is those all the models I told you about from the end of the 80s, my bicrossproduct model with Ruegg, and the earlier one, the Planck scale model, especially this idea of bond reciprocity, etc. They were all done before we really had a good knowledge of differential calculus. They were done for flat space models. So I would like to suggest that all of that could be revisited with curved models using actual quantum differential geometry as we now have it. So introduce quantum differential calculus, revisit those models. And then when we do that, we should be able to try to relate things like observable state duality, where you're talking about states and look at pure states and mixed states and gravitational decoherence, try to relate it to entropic ideas of which relate entropy and gravity. So I think there's a whole nexus of ideas there which we can begin to explore. Now in this paper here, I do particle creation on Z. That's not quantum gravity, that's semi-classical, that's a Hawking type calculation, but that can certainly be done. But that tells you that you could begin to do thermodynamics. But there's a lot more we need to understand, but the real understanding would come out of quantum gravity. For the differential calculus, this paper in Journal of Algebra with one of my other students, Ryan Aziz, tells you the natural differential calculus on bicrossproduct Hopf algebras. I mean, there's a very natural one to take. So that can certainly be pursued. Then one could look at, so the whole stuff I haven't told you about, I'm sure other lecturers in other talks in this series will cover it, but there's a whole world of noncommutative geometry based on cyclic homology and Fredholm modules and such things. In particular, he's got a notion of Dirac operator, which we call a conspectral triple. And the question is, when do they intersect the constructive approach that I've described, which I call quantum Riemannian geometry? So there is quite often a QRG realization. So there's one example for the Q-deformed sphere in a paper. Well, it's in the book, in fact. It's also in a paper with Edwin Beggs. But one could apply it for many others. In particular, one can revisit the bicrossproduct model to find the correct Dirac operator on the curved bicrossproduct model. I think that would be a nice problem. I'm sort of angling here for anyone who wants to work on these things. By all means, email me if you're interested in more details. Then I think to really understand about Einstein tensor, well, to really understand the physics, right? How do we really understand the physics of gravity? Of GR? Well, we have to look at geodesics. So on a curved noncommutative background, we need to understand quantum geodesics. Now, there is a framework for that, which was introduced by Edwin Beggs. It's in his paper to appear. It requires bimodule connections, but now in a more general setting. So that could be computed for the models that I described, for the fuzzy black hole, for example, and many others. And then we would really like to understand Einstein tensor and stress tensors. And this is very much in the dark. But what's really missing is we don't have any idea of variational calculus in terms of a Noether theorem and with how it would link up with the Hamiltonian quantization in, let's say, the BRST formalism. So we really would like to understand that so that we're not just guessing about the Einstein tensor. And then I would just like to end by saying that this was all in the context of Planck scale physics, which was my mission today. But it's just mathematics. So this quantum geometry can be used anywhere where you might have noncommutative coordinates. In particular, in ordinary quantum mechanics on phase space, you have noncommuting coordinates. So you can explore the geometry of Riemannian geometry, not just Riemannian, but symplectic, quantum symplectic geometry, quantum differential geometry of all types on actual quantum systems. And one thing in that direction is the paper with Edwin, which exactly shows you how you can use you can formulate ordinary unadulterated Schrodinger's equation, so the one from 1920s, but write it as a quantum geodesic flow on a quantum space using Edwin's bimodule connection formalism. Okay, so I think, so there's lots of scope there to apply this to atomic systems and connect it up to quantum information and quantum computing. So that's how I see things going forward. Okay, so I would like to stop there. I've had my full hour.